In this video, we will start an introduction to confidence intervals. And first, before we start actually creating the confidence intervals, we will discuss the process of and the thinking behind obtaining a confidence interval. As a point of reference, if you are interested in the textbook sections, we are in Unit 8 of the Introductory to OpenStax book, and section 8.1 is what we will be doing here, which is a single population mean using the normal distribution. And in the IntroStax Corequisite book by Lumen, we are in Module 8, Confidence Intervals, and we are in the section Intro to a Single Population Mean using the normal distribution. So what we will be doing here is we will try to estimate a population mean given a sample mean that we have calculated. I want to remind you that the sample mean is a variable that for large samples is approximately normally distributed with a mean equal to the mean of your variable and a standard deviation equal to the standard deviation of the variable divided by the square root of n, with n being the size of the sample that you are collecting. However, we are not going to look exactly at applications right now. Right now, we will just discuss this concept. So if we remember, we have discussed that given large sizes of n, sizes greater than or equal to 30, the sample means distribution follows a normal distribution. So, and that was regardless of the underlying distribution of the population. And that just required that we are looking at a sample mean. So we know the size of the sample and we are all collecting samples of the same size. We are all asking the same question about a numerical variable, and we are all calculating the mean from the sample. So the confidence interval is our attempt to ensure that the population mean is close enough to our sample mean, and we can kind of guess approximately where the population mean will be. So this is our first step at inferential statistics, and we will go a little backwards in order to understand how the confidence interval works. So if the sample means follow a normal distribution, that normal distribution will have the mean of the population as the mean of the distribution. So this z-score of 0 will correspond to the mean of the population, which is the mean of the data and also the mean of the distribution of the sample means. And there are three popular confidence levels. We want to be 90% confident that we have captured the mean of the population. We want to be 95% confident that we have captured the mean of the population, or we want to be 99% confident. In other cases, there are different confidence levels, but these are the most popular ones. So when we are at 90% confidence level, then we assume that we have the distribution of the sample means, which is normal. We will use z-scores here, and we want to know what is the middle 90% of sample means we could ever obtain. So I'm going to use art of stat. I'm going to use a normal distribution. I will go under find percentile quantile. I will leave it as the standard normal distribution with a mean of 0 and a standard deviation of 1. So I will be getting the normal curve with 3 tick marks to the right of the mean marked as 1, 2, 3, and 3 tick marks to the left of the mean marked at -1, -2, -3. And you see here that under the z-score of 0, that z-score corresponds to the mean. So for the percentile, I'm going to do a two-tailed test, and I want a two-tailed interval, and I want 90% of that to be in the center. And you see here that the two z-scores that are symmetric about the mean are 1.645 away from the mean. So the bounds of the confidence interval for 90% are 1.645 standard deviations to the right and -1.645 standard deviations. That is 1.645 standard deviations to the left. If my confidence level is 95%, then the mean will be located in the middle. This is the mean of the data and the mean of the distribution of the sample means. And I want the central probability of selecting a sample with a mean within the 95% in the middle will be from 1.96 to the right to 1.96 to the left. These are numbers of standard deviations that I fall away from the mean. And if I want a 99% confidence level, that means I'm looking for 99% of the samples to be to have a mean coming through this interval. I'm going to change the central probability to be 99, and I am at z-scores from 2.576 to the right, to the left, up to 2.576 to the right. And again, remember, this is how many standard deviations your value will be away from the mean. So the level of confidence, the 90, 95, 99, or any other level that they are giving us, indicates that we assume that our sample will come from the middle likely samples at the confidence level percent of the time. So that if we collect 100 samples and we have a confidence of 90%, we expect 90% of our samples, the 90 samples, to actually have a mean within 1.645 standard deviations of the actual mean. If we have a confidence level of 95%, we expect out of 100 samples, 95 of them to have a mean within 1.96 standard deviations away from the actual mean. And at the 99% confidence level, we expect 99 out of 100 samples to have a mean within 2.576 standard deviations away from the actual mean. So at a given confidence level, this is the 90% in the first graph. We assume that 90% of the times we will get a sample that has a mean within the interval of likely values. So we expect our mean to be here, here maybe, it could be here, it could be here, it could be very close to 0, it could be as far away as 1.645. So the question is, how far from the mean, the real mean, the population mean, that's the parameter, is our sample mean, which is a statistic? And the answer is that this distance will be less than 1.645. So we will be between negative 1.645 and positive 1.645. And that will be the distance between the mean and the sample mean, the population mean and the sample mean. And then the question then is, how far from the sample mean is the real mean? So if you don't know the real mean and you are trying to find it, but you have calculated the sample mean, so let's assume you calculated this value. how far away from this x bar is the real mean? What is this distance? And the answer is this distance is also less than 1.645. So if the distance from the mean going to x bar is less than 1.645 in absolute value, then the distance from x bar going to the mean will also be less than 1.645 in absolute value. Or if we were to take it in any value, this x bar minus the mean would be between negative 1.645 and positive 1.645. Assume that we are at the confidence level of 95% and we have a usual sample, a sample that 95% of the times will be within the interval of confidence. So let's say that our mean is over here. How far away from the parameter is this sample statistic? And the answer is it will be less than 1.96 in absolute value. And then how far from the sample mean is the real mean? And the answer now is that going in the other direction, I am still less than 1.96. So in absolute value, the real mean is less than 1.96 standard deviations away from the sample mean I calculated 95% of the times. And in terms of regular numbers and not absolute values, this difference will be some positive number less than 1.96 or some negative number greater than 1.96, approaching, coming closer to 0. And if you're at the 99% confidence level, 99% of the time your sample mean will be less than 2.576 standard deviations away from the mean. And that also means that if you know your sample mean, which is the only value you know, you can guess that the mean will be less than 2.576 standard deviations away from your sample mean. And again, the difference between the statistic and the parameter will be some value less than 2.576 standard deviations and greater than negative 2.576 standard deviations. So as we are creating a confidence interval for a population mean, if we know the standard deviation, which will result to the fact that we know the mean follows a normal distribution, we can be 90% confident that the real population parameter, the mean corresponding to a z-score of 0, will be less than 1.645 standard deviations away from my sample mean that I have calculated. 95% of the times it will be less than 1.96 standard deviations away from the sample mean that I calculated. And 99% of the time, the real parameter, the real population mean, will be less than 2.576 standard deviations away from the sample mean. These standard deviations are the standard error of the sample mean, so they are actually the standard deviation of the distribution of the sample means, because we already know that the distribution of the sample means has a standard error that it gets smaller as the size of your sample gets larger. So we are no longer talking about the standard deviation of the variable. We are talking about the standard error. The standard error is the deviation of your sample mean from the actual population mean.